A graph of our demo here. Right, so we have them trading water back and forth, representing reactive products. We've got reaction progress down here. Okay, and on this side we kind of have the general amount of products and reactants. So just to kind of give us a sense of scale, I'm just going to say, all right, we have 10, 5, and 0. Okay. All right, so let's represent the gray line will represent the products. The blue line will represent the reactants. Okay. So where do the reactants start here? Where do we start out? The top, right? It started at pretty much 10, right? And then where do we kind of end up in terms of the reactants on a scale of 0 to 10 in terms of that bin right there? What do you guys think? 4? What's that? 6 and 4. That works. Yeah, 6 and 4 works, right? It's not equal amounts, so we have different amounts. Okay, so reactants we end up with 4. So let's say they started trading, and over time kept decreasing, then finally, right? They got to that point and just leveled out. Okay, what about the products? Where did the products start out? At 0 and ended up like 6, right? Okay, so we start at 0 and we keep going, kept exchanging. And there we go. It levels out. All right, so at what point did we reach equilibrium? At what point did the reaction reach equilibrium? Yeah.
Like once after they intersect, and then like they're at like a steady like opposite of one another or something.
Well, the intersection doesn't have to do with anything. That doesn't matter. Second part of what you said matters in terms of equilibrium. Right.
Just like equilibrium when they both even out, right?
Right. Just right when the lines steady out. Okay. Once the amount of reactants and products no longer change, from that point forward, we're at equilibrium. Right. Okay. So that's like from about right here. All right. From that point forward, the reaction has reached equilibrium. All right, so the amounts of reactants and products stay steady. They stay constant. Did the reactions stop happening? No, they kept trading water back and forth, back and forth, back and forth. The reaction's still happening. But the amount of reactants and products is constant. That's equilibrium. Okay? That's when equilibrium is reached. Once the amounts of each stay steady. Now, a lot of reactions that you've seen to this point, you form a lot more products than you do reactants. Okay, pretty much all the reactants, 99.99% of the reactants get converted to products. Okay, but there's still a little reversibility there. There's a small amount that goes back the other direction. Okay, but it's just a matter of once you reach that equilibrium, you can't even really tell. You don't see the reaction going back and forth, right? Here we can see them exchanging the water. Back and forth, back and forth, back and forth, right? But at the atomic level, that's still happening, but you're observing it. It looks like nothing's changed anymore. Okay, all right. So there still is an equilibrium that is developed. Okay, so do not fall into the misconception that that is the equilibrium. Okay, because we could draw another graph very similar to this, right, where the lines don't cross. Okay, so like for example, just real quick, something similar to that, right? We could do something very similar and be like, oh, well, it starts here, bubbles off, starts here, levels off right there. Lines never cross, but we still, from this point forward, you're at equilibrium. Okay? All right? So just understand, once they level off, that's when we reach equilibrium. Okay, so that's the key component. So chemical equilibrium is established once the amounts of reactants to products, or once the amount of reactants, I should say, and products stays constant. All right, and this is a dynamic equilibrium. What does it mean to be dynamic? Where have you heard someone be described as dynamic before? Okay, so have you guys ever seen Ferris Bueller's Day Off? Yes, okay. Do you remember Ben Stein is in the movie and he's the high school teacher? And he's standing in front of the classroom and he's teaching economics and he's like, yeah, he's like, and he's like, you know, whoever the president was, described it as blank, DOO economics. Anyone? Voodoo economics. And that did that raise or lower? Anyone? Raise the level of income, right? So very monotone, not dynamic, right? Okay, dynamic speakers all over the place. They can do everything. They're constantly changing. Things are always happening, okay? When we're talking about a dynamic equilibrium, the reactions are still taking place, all right? Things don't stop once you reach equilibrium. The chemical reaction is still happening. It's dynamic. Okay, it's a dynamic form of equilibrium. The rate of the reverse reaction is equal to the rate of the forward reaction. Okay, so dynamic equilibrium just means that the reaction is still occurring. Okay, the reaction is still occurring. It's just that the rate of the forward reaction, all right, when we say the rate of the forward reaction, we're talking about reactants going to products, is equal to the rate of the reverse reaction right? And that is when I'm still going to write reactants and products on the same time, but notice the arrow, okay? The rate of the reverse reaction are equal to one another. So if you're forming products just as quick as they're breaking down to form reactants, the amounts of each stay the same, and they're constant. They stay steady, okay? All right, so that's a dynamic equilibrium. So when the reactions are still happening here, okay? Are we good with that? Okay. All right, very good. All right, now equilibrium can favor one side or the other. Okay, in this case, our equilibrium favored our products. In some cases, our equilibrium will favor our reactants. Okay, so equilibrium can favor reactants or products. Okay, so an equilibrium is represented by K. It's called KEQ. And they put the little EQ down there for equilibrium, and K is just our constant. Then all it is just it's the relationship of products to reactants. Okay? It's just pretty much the ratio of products to reactants. That's what it boils down to. Okay? So if K is greater than 1 at equilibrium, what is favored? Reactants or products? K is greater than 1, what's favored here? Which one is there going to be more of? Okay. Products. Yeah. Okay. There's products. K is less than 1. The reaction at equilibrium will have more reactants. If K is equal to 1, neither is favored. Okay, neither one is favored. That's very, very rare. An equilibrium constant equaling 1, that pretty much never happens. Okay. I don't even know one offhand, to be honest with you. I can't even give you an example of when that's the case. I don't know one. Usually, it's so far one direction or the other. Okay, like things that are very insoluble, like that form of precipitate. Those have Ks that are really humongous. Like they're not just a little greater than 1. I mean, they're like on the order of times 10 to the 15 or something. Okay, that's how much the reaction favors the products. And that, to us, that looks like, oh, all the reactants get converted to products. And pretty much almost all of them do. But a real tiny fraction of them don't. Okay? So when things are insoluble, like when you can't get something to dissolve, okay, K is like times 10 to the minus 23. That's how small it is. So it looks like none of it's going into solution. Actually, the reality is there's probably a tiny amount of ions that are floating around the solution, even though it looks to us like nothing is dissolving. Okay, so typically right here, this is never, it's pretty much never. Okay. All right, so speaking of equilibrium constants and kind of finding numbers and stuff, we need to write some equilibrium expressions. Okay, we got to practice writing equilibrium expressions. Okay, equilibrium expressions. So we're going to get our expression from our balanced chemical equation. All right. So the general formula is this right here. So if we have some reaction A plus B going to CD, right? When we set up our equilibrium expression, right, we get products over reactants. Concentration, oh, whoops, that's A. Concentration of B, right, B, there you go. Okay, so typically we're looking at concentrations. All right, so we're going to use concentrations, or you can use pressures. Okay, if these are gases, you can use pressures. If they give you the pressures of stuff, we can use pressures. But typically, you're going to get these values of each one of your reactants and products in terms of concentration, because you're looking at their concentration in solution. Remember, what's one of our factors that affects the rate of a reaction? Okay, what are the factors that affect the rate of reaction? Okay, heat, temperature, right? Concentration, yes, concentration's one. What's pressure? Oh, hey, there's another one, right? That's why we can use pressure goes in equilibrium constants. Surface area, okay, good. All right, so a lot of times you're going to be given concentrations for these guys, or we can calculate concentration because we just came out of the solutions unit, right? So you can find the moles divided by the volume. Boom, we get concentrations. Isn't that nifty? Okay. All right, so but today we aren't going to calculate any equilibrium constants. We won't calculate any Ks. All right, we're just going to practice writing the equilibrium expression, okay? Because there's a couple little things in here that are going to be important. Is we don't include solids or liquids, okay, in the expression. Okay, if they're gases or they're aqueous, you put them in there. If they're solids or liquids, we aren't going to put them in there. All right, so let's do a couple examples here. So I'm just going to start. These are gases going to 2SO3. Okay. One. How about AgNO3 silver plus KCl aqueous, AgCl solid, NO3 aqueous. I got some more around here somewhere. Find a few more that I wrote down. About 2NO2. There's 4 of them. Oops, then 2O2. These are gases. All right, so when we write these guys out, okay, so does anybody want to take a stab at the first one here? Oh, come on. You got the general formula for all gases. Dial it up. Katie Canlin, all right, let's do it. What do you got?
SO3 to the second
Okay.
over SO2 to the second.
Yep.
And then O2.
There you go. Good job. All right, that's it. That's it. Okay. We're going to try the next one. No solids included. Yeah, prevail. Hang on 1 second. AgCl. That guy's a solid. Sorry, this is an S.
KNO3.
Okay.
AG NO3 squared.
Why do you want to square it? It doesn't matter. It's just a 1, right? There's the A and stuff are just the coefficients, yeah.
And then
KCl, good. There we go. Why does it keep doing that? All right, so don't let, these are just 1s, right? The coefficients are just 1s here, so you're just raising them to 1 power. So there's still a 1 up there, but you don't need to include that, right? All right, Tori, what about the next one here? What about this one? These are both gases.
would you do NO?
Okay, products over reactants, right?
Right. Okay. So it would be N2
Yep.
over NO2.
And then you can't forget about the coefficient. So you gotta square that guy. Okay. Last one's a tough one. What do you think, Sarah? You think you got it?
Is it just O2?
Not quite. No. It's 1 over that. Okay, it's 1 over that. Since there are no, since it's a solid there, since the iron oxide's a solid, it's not included. But the reactants, right, the one reactant that we include in there is O2, still goes in the denominator. Okay, you still have to put it in the denominator, so we just put a 1 over it. Okay. How about, this is a good one. I'll put 2 more up here. All right, write the KEQs for these last 2 here. Always products over reactants. Kylie, what do you want to do for the top one?
Do 1 over
There you go. Okay, good. What about the last one? Yeah.
CA2 plus and CL minus squared over 1.
Yeah, over 1. Or you can just leave it like that. Yeah, you don't have to write the over 1.
I have a question.
Uh-huh.
How do you get from just like the names of the elements to figuring out the number?
All right, they're gonna have to give you. They're gonna have to give you information, right? They're gonna have to tell you about. Oh, we have this many moles dissolved in this much, this many liters of solution, right? And then you can get moles divided by liters because of concentration. right? You can plug those numbers in and kind of go from there. Okay. Oh yeah, that's tomorrow. Yeah, yep. Oh yeah. Sir.
Not all reactions can go like back and forth, right?
Not all of them, but a large majority of them can. Yeah. Yeah. It's just a matter of usually the reactants are heavily favored or the products are heavily favored, so we see that as no reaction happening, or we see the reaction going to completion, right? And that sort of thing. So,
What about combustion? Does it open?
well, it's awful hard to go back the other direction, right? So in some cases, the rate of the reverse reaction is either so slow or not possible that it is a one-directional sort of thing. A lot of times, most reactions that take place in solution are reversible. They have a reversible component to them. Okay, but like you said, a combustion reaction is a good example of kind of a reaction that isn't reversible. Yeah, it's kind of a one direction sort of thing. Okay. All right, good. Great. All right, well then, on to the homework. Yes. I'll pass it out right now.